Hi, this is Mikey with the DLASC, and in today's video, we're going to be going over rational expressions. So, whenever you think of a rational expression, or the word rational in general, that's always, of course, going to have to do with fractions, right? So we have, fractions like 1/3 or uh, 2/7, or even famous ones like 22/7, which is an approximation of pi. But what we have in algebra when it comes to rational expressions is we have ways of determining where these expressions will be defined and where these expressions will be undefined, like what values of x that we can find where these graphs will start to approach zero or start to approach infinity or negative infinity. And I'll just be going over some of the conceptuals of that today. So let me show you what I'm talking about. So to start off, we're just going to use a simple rational expression, right? So we'll go 4x plus 20 over, let's say, x squared plus 12x plus 35. All right, so we're going to use that. And what we're going to do is we're going to do three things. We are going to solve for the zeros of the expression. We are going to simplify the expression, and we can go ahead and graph it as well. So let's go ahead and simplify this expression, right? That'll be our first step. So what we're going to do is we're just going to factor this, right? So if we see any prominent factors we can take out, we can do the numerator first, right? So we're going to do 4x plus 20, and that can be broken down. We can take a 4 out of there, so 4 times x plus 5. And now let's do the denominator. So we have x squared plus 36x plus 35, right? So we can find factors of 35 that we can add together to make a positive 12. So let's see. So we have 1 and 35, and we have 5 and 7, and those factors together, if you add 5 and 7, they equal 12. So that means that our denominator, that quadratic equation, we can break that down into x squared plus 5. We can break that down into x plus 5 and x plus 7, right? So now that we've broken that down, right, we can see we do have similar terms in the numerator and, right? So that means that here, for this x plus 5, what we can do when we're simplifying is, it's very simple. We can just take them out, right? Because they'll cancel out through that rational expression. And what we'll be left with is 4 over x plus 7, right? That's pretty simple. So that's going ahead and simplifying rational expressions. But what if we want to find the zeros, right? What if we want to find where these expressions are undefined, right? So what we'll do is we'll use the same equation. Do 4x plus 20 over x squared plus 12x plus 35. And we're going to go ahead and do the same thing, the same first step. We're going to go ahead and break this down, right? So we'll break this down again into 4 times x plus 5, right, over x plus 5 times x plus 7, because remember, we can take 35 and break it into its factors. And if those factors add up to our b term, because remember this is ax squared plus bx plus c. If the factors of c can add up to its b term, then we can split that quadratic into two separate expressions. So now that we have this expression right here, right, this can be used to determine where the function is undefined, where we have zeros, right? So what we define in mathematics as undefined, right, that is going to be wherever there is no value, right? Wherever we can't compute that value. And for rational expressions, it's really easy to see those values that are undefined because remember, whenever you have fractions, the denominator always has to be greater than 0, right? The denominator always has to be greater than 0. So it could be said that whenever the denominator is not 0, that means that we have a real value. But whenever the denominator is 0, that means we've run into a problem, right? When the denominator is 0, then that means that our function is undefined, right? So we can do that here. We can see where it's going to be 0. So we can take x plus 5, right, and set that equal to 0 to see what value of x makes it 0, right? So x plus 5 is equal to 0. And we'll go ahead and solve this, right? So it's just a quick rearrange. That means x is equal to -5. And so we'll do the same thing for x plus 7. And this will be another quick rearrange. Real quick, x equals -7. So that means that for our rational expression up here, that means that if you try to graph it, these values, these specific values, x equals -5 and x equals -7, will not have a solution, right? So we can say the expression for x plus 20 over x squared plus 12x plus 35 is undefined at x equals -5 and at x equals -7, right? And that's how we would answer that question if it were to be given on a test or if it were to be given on a quiz or homework or anything like that, right? You would just write that answer out. Now, when it comes to graphing, right, graphing is going to be a slightly different story. All right. So the whole reason that we go through everything, going through simplifying those rational expressions, breaking down the denominator of those rational expressions, finding where it's undefined, right, is so that we can end up graphing it. And whenever we're graphing, we can actually take those points that we found as undefined, and we can go ahead and translate those into what are called asymptotes, right? So asymptotes are going to be any place where the graph is undefined. And so here, we can go ahead and take our graph, and I'll show you what I mean. We'll take our graph, we'll do 4x plus 20 over x squared plus 12x plus 35, which we know is 4x plus 20 over x plus 5 times x plus 7, right? And so we're going to go ahead and we're going to draw our graph. So since everything is going to be within the negative quadrant, we're going to go ahead and draw our axes here. Here, let me move that axis up just a bit. And here, let's put that axis right there, right? So asymptotes, we can draw on the graph to represent them in this way, right? We know for a fact that there's going to be no value of y at that particular value of x. So we will just draw a dotted line that our graph will not touch, right? So at x equals -5, so we'll do 1, 2, 3, 4, 5. We'll do an asymptote right there. And at x equals -7, 6, 7, we'll do an asymptote right there. And our graph will never touch that, right? So let's go ahead and let's do some plotting, right? So we will go ahead and do and plot a couple of points. So we're going to start with 0, obviously, since we want to see exactly where this graph is coming from. So we'll start with 0. We'll go 4 times 0 plus 20, right? That's going to be 20 in the numerator, and 0 plus 5 over and times 0 plus 7. That's going to be 5 times 7. So it'll be 20 over 35. So 20 over 35. If you divide those by 5, that is 4 over 7, right? And so, I don't exactly know where that is, but I know that it's probably going to be a little bit slightly above 1/2, right? So let's plot that point right there. And then we can do 1. So 4 times 1 is 4 plus 20, that's 24. And we'll do, here, I will outline this in a table. So when x is 0, 4 over 7. When x is 1, then we'll do 24 over 6 times 8. It's 48. So it's 24 over 48. That is 1/2. So we can see where that graph is going, right? But now we can get into the real meat of the show, right? So we're going to go ahead and we're going to do a -1. All right. So now that we have these points leading up to this first asymptote, right, we can tell that because of the direction and the flow of how these points are moving, we can go ahead and say right now that, and forgive my shaky hands, but that line is going to be moving towards the asymptote, moving up towards infinity, right? And so we can go ahead and we can get points for the other side of the asymptote as well. So let's go ahead and let's do, let's say if x is going to be 5.5, right? All right, and so we can see that this middle section looks a bit like that, right? We can see where that came from because of these points. And let's see here. Let's go ahead and get the points for this last section, right? Ignore all my math in the background. Here, let me clean that up for you. So now you're able to see, if we go ahead and plot this graph like normal, avoiding the asymptotes, because they'll give us zeros, then this graph is going to end up looking something like this, right? And that is essentially what asymptotes are. Asymptotes are places where the function is undefined and where you cannot map a value onto, but it defines where your function, whenever you're graphing it, where these pieces of your function will move towards infinity or negative infinity, right? So here, this moves towards infinity. Here, this moves towards negative infinity. Here, it moves towards negative infinity. And here, it moves towards infinity, right? And of course, on the sides here, these sides go towards 0. And that is graphing a rational equation. Again, my name is Mikey from the DLASC, and I hope that I was able to help today.